Hello and welcome to episode 2. Today we're digging deeper into the layers of Earth. We outline what each layer is, what are they composed of, how they formed and when, and why on Earth are they important.
Very nice.
See what I did there?
Yeah, very nice. Actually, I have a fun fact I want to share straight off the bat from last week. So last week we were talking about rocks and minerals and things like that. And I don't know if you've heard of corundum. So corundum is a mineral, so this is a crystalline solid, right? And all it is aluminium oxide. So 2 atoms of aluminium, 3 atoms of oxygen in its kind of base unit. And it's actually a very hard mineral, and I use it in my research to do polishing. But it's also what forms rubies and sapphires. So they're exactly the same mineral, but they just have different trace elements in them. So rubies have chromium in them that's substituted into kind of vacancies, whereas
This is an unbelievable fact to begin with. What is going on here? We're talking about the layers of Earth. Welcome to the core of everything. Right, so let's get cracking. So, what are the layers of Earth? Well, the Earth is 6,378.1 kilometres, a radius on average. It's not a perfect sphere, so it's wider at the equator than at the poles. So, if you took your hands and put one on the top and one on the bottom and give it a slight squeeze, that's what you get for the Earth.
Yeah, so we would actually call that an oblate spheroid. So it's a little bit like a lentil or a Smartie or even a minstrel. Do you remember minstrels?
I meant minstrels.
I don't know if they're still around.
They're not my cup of tea, but yeah.
Fair. Anyway, there's about a 20-kilometre difference between the radius at the equator and the radius at the poles. So actually, if you're standing at the equator, you're further away from the centre of the Earth than if you are at the North or South Pole, and that's due to something we call the centripetal force. And you can imagine that as if you are in a car going around a bend. So the force is acting along the radius from the corner, from the centre of the corner out towards the car. And as you go round that bend, you feel like you're being thrown out. And that's the inertia. And that inertia has a name. It has an apparent force. It's called the centrifugal force. So there's a little difference actually between the centripetal force and the centrifugal force. The centrifugal force is what it feels like, an apparent force on our bodies, but the actual force at play is the centripetal force that's pushing us out. And that's exactly the same as with the Earth. So as the Earth's spinning round, there's a centripetal force acting, pushing that material further out around the equator, which is why the equator is about 20 kilometres wider than the North and South Pole.
So is that when you're driving around a bend, the passenger's then leaning to one side?
Yes, yeah, exactly. Yeah. And if you're sitting in the middle, you'll get crushed.
Yeah, exactly, yeah.
Yeah.
That's interesting.
So the Earth has 4 main layers. Going from out to in, we've got the crust at the surface, then we have the mantle, then the outer core and the inner core.
Yeah, so we have the inner core, which is solid and made of iron and nickel, and that's about 3/4 the size of the moon. So 759 miles in radius, which is, 1,200 kilometres. And then you have the outer core, which are iron and nickel again, but it's fluid. And that's around 1,400 miles thick. And then you go into the mantle, which is our thickest layer. It makes up about 84% of the Earth's interior, and that's 1,800 miles thick. And it's hot and viscous. It's like porridge, and this is just all hot, melted rock. So yeah, I think people say porridge or caramel. At its hottest, it goes up to 3,700 degrees Celsius, and towards the crust, so as you work your way shallower, it actually drops in temperature. And then you get to the crust, which is super thin in comparison. So if you imagine the mantles being 1,800 miles thick, on average, the crust is 19 miles thick on land, but under the oceans, it's 3 miles thick, 3 miles deep. So it's really, really thin. So I think, like Brian Cox once said, in proportional terms, that if you imagine, bear with me, if you imagine the Earth is an apple, the crust would be the skin.
That's a really helpful image.
Cheers,
actually.
Thanks,
Shout
Ryan.
out.
You're done
yeah.
now. Yeah,
I'm sure he's listening.
No, he's just left.
Oh,
That was him,
I see. Sorry. See you, Brian.
But it's really...
I'm a bit late to that.
Yeah. But it's a bit weird that we are treading on this thin layer above molten rock, like the Earth's a bit like a creme brulee.
Actually, if you were on Mercury, it would be even more the case because with the numbers you've just given, the core, the inner and the outer core, so the core makes up about 50% of the Earth by kind of that radius going from out to in, whereas on Mercury, the core makes up about 85% of Mercury's volume. So it's actually a huge amount, and they've been able to detect that by looking at Mercury's gravity and the magnetic field and things like that, because the core affects those things, which we're going to talk about a little bit later on.
Yeah. Does it have a magnetic field?
I think it does have a magnetic field.
Oh, okay.
Maybe a weak one, but they've definitely. But I could be wrong. Maybe a strong one.
Yeah.
I wouldn't want to commit.
Yeah. Nice. Okay. So yeah, but the Earth's like a creme brulee. Great. So we have our inner core, outer core, mantle, and then crust. But how do they all form?
So we started off with the Earth, and the Earth is actually older than its core. So the Earth is about 4.54 billion years old. So kind of just with a quick overview, we had a solar nebula. So that's kind of the early sun forming in a big cloud of gas and dust. And over time, that kind of progressed into a swirling mass called the protoplanetary disk. And within that, there are perturbations that gradually bring that gas and dust together to form our planets. Now, the Earth used to be a uniform ball of all that material, but over time, due to increasing temperatures, changes happened to how materials were distributed within the Earth. And that temperature increase came from a couple of sources. So one of them was the leftover heat from planetary formation. So this is due to collisions of all the building blocks that made the Earth, accretion, so those things sticking together, and the compression of those building blocks. So we get heat from that. But we also get heat from radioactive decay within the Earth. So we have elements within the Earth that are decaying, things like uranium, thorium, potassium, and as those decay, so basically that means that they change from one particular form of that element, maybe into another form. We would call those isotopes. So they just change in mass or even into different elements. And as that transition happens, we release energy. And that energy is heating up the Earth. And that increase in energy gives us an increase in temperature. And that allows us to reach something called the iron catastrophe after about 500 million years. And this basically means that we get to a point where temperatures are high enough to melt that iron that is currently distributed in the uniform ball of the Earth. So when we can melt the iron, things can start to move around. And basically we get iron, nickel, and other heavy elements sinking to the core because they're denser. And we end up forming nickel-iron alloys at the centre of the Earth. And actually we get other elements kind of joining them, so precious metals, things like gold, platinum, and cobalt. We would call these siderophiles. That just means they like being with iron. They also differentiate, so they follow that iron and nickel into the core. They're dissolved in the core, as well as sulfur actually as well. So we've got these elements kind of forming our core.
So as a quick summary, you have a large ball of rock that when it starts to melt, the heavier stuff falls to the bottom.
Exactly.
Essentially, and you get these layerings.
Yeah.
Okay, and then last week, or the last episode, we were talking about the geothermal gradient. So how, because that's when the temperatures get hot as you go into the Earth. So how does that tie into this formation?
Yeah, so that kind of heat that I talked about in the Earth, that is what is fueling this geothermal gradient. So that's kind of about a 25 degree change every kilometre. So that heat is fueling that geothermal gradient, and it's mostly powered by radioactive decay of elements within the core and the mantle. So we have our core that's made of liquid, iron, and nickel. So the inner core, we actually think it behaves as a plasma. So it's basically a pressurized liquid. So it's not able to form, because it's so pressurized, it's buried so deep under so much mass, under so much gravity, that it's not able to form a solid. So we're actually forming a plasma. And scientists recently found that it seems to be growing by about 1 millimeter per year. And the question is, well, what is causing it to grow? And we think it's because it's cooling and it's freezing over time. So it's changing from this pressurized liquid, this plasma, into a solid. And you can just think about when you make ice, for example, you don't fill your ice tray up to the brim because when water freezes, it expands. And that's exactly the same as what's happening with the inner core.
I mean, do we know, is there anything to do with how long this is going to take for it to freeze? Or like, you know, I'm assuming that's millions and billions of years.
Yes, I don't think we'll see it within our lifetimes, but it is a discernible change. But we also think there is an inner core. So our inner core is aligned north-south, and that's what gives us the magnetic field around the Earth that's aligned kind of mostly with the north and south pole. But the inner core, scientists think that actually there are crystals that are oriented east to west, so about 90 degrees to that north-south, which is really interesting. So actually the structure and the dynamics of the centre of the Earth are very different to what we thought they might have been.
Okay, great. So we've got a solid inner core, a liquid outer core, and then you've got this big area called the mantle, which is 84% of the Earth's interior.
Nice, yeah. So the mantle is mostly made up of heavy metals. So we've got some iron and nickel in there again. We've also got magnesium, and then we start to get our silicates. So these are the majority of the kind of minerals that we see on the Earth's surface. So they're made up of silicon and oxygen, kind of base units repeating. And remember, that's what our definition of a mineral is. It's a crystalline solid with a repeating order. And two of the most prominent ones in the mantle are olivine and pyroxene. And we actually do see these minerals at the surface. Now, the mantle spans a huge temperature gradient. So we have about 1,000 degrees at the surface of the at the top of the mantle, where it meets with the crust, and then down where it meets the core, it's about 3,700 degrees. So there's a huge temperature increase there.
And the mantle isn't just one massive body, it's actually made of sort of parts. And in the upper part of the mantle, there's something that geologists like to call the asthenosphere, which is when it gets a bit colder, there's a point at which the mantle starts to become ductile and sort of semi-solid. And then above the asthenosphere, we've got the lithosphere. And the lithosphere is composed of the most upper part of the mantle, which is sort of brittle and a bit more solid, and the crust, which is what we reside on as humans. And the crust formed, well, initially the crust was an ocean of magma on the surface of this upper mantle. As the Earth cooled, the whole surface crystallized and solidified into what we see as the crust now. And the crust is made of oceanic crust, which is found under the ocean, and continental crust, which is land. And oceanic crust is your igneous rocks, like we discussed last time, like basalts. And then you have our continental crusts, which is like granite, which requires the presence of water.
Yeah, so our oceanic and continental crust are also a bit different in terms of their thicknesses and their densities. So oceanic crust is normally between about 5 and 10 kilometres, whereas our continental crust is about 30 to 50 kilometres, even reaching up to sort of 80 kilometres at the thickest points. But our continental crust is actually much less dense than our oceanic crust. And this means that if our oceanic and continental crusts meet and collide, our oceanic crust is going to sink down below that continental crust because it's more dense.
Right, and that's when you form mountains and stuff.
Yeah, and you get volcanism too.
Yeah, exactly. But speaking of this sort of stuff, I was listening to Neil deGrasse Tyson the other day, and he was on the Joe Rogan podcast. And he's the famous American astrophysicist.
Yeah.
And he was talking about how if you shrink the Earth down to the size of a billiard ball, or billard ball, how do you pronounce that? Billiard ball. With all its trenches and its mountains, it would be smoother than any ball ever manufactured.
Okay.
Right? Now, if you look at the Marianas Trench, which is 7 kilometres deep, 11 miles, and Everest, which is 5.5 miles tall, which is 8.9 kilometres tall, from top to bottom, that's 12.5 miles. But if the Earth was the size of a billiard ball, that would mean that Mount Everest would equate to 0.04 millimetres high,
Okay.
and the Marianas Trench would be 0.05 millimetres deep on that tiny little ball.
Yeah.
right? So yes, that would probably fit inside the dents and bumps of a normal ball. So the legend is correct.
Okay.
But I have a problem with it because he talks about it being smooth. And if you say you remove the water from Earth, which obviously in this case you would have to, or it would be a very wet ball,
Yeah. Yeah.
it wouldn't feel smooth. It would feel rough because it's a rocky surface.
But it isn't smoothness just a function of effectively height difference on a surface?
Maybe, but I thought it must be something to do with human touch. And if you run your finger over the Earth, it's rough, isn't it? If you were to touch a rock, a lot of the times it's rough, isn't it? Like a sandstone or something.
But if you were to touch a really tiny rock, I don't think you would notice that it's rough.
I think you're wrong, and I think Neil's wrong. But if he has any contention, then Neil, give us a call.
Just to be clear, Neil, I'm on your side here. Please don't come at me.
We can get Brian back. Brian.
Oh, I think he's gone.
I think actually Jack's correct. Yeah.
So when did the timing of all these changes come about?
Well, you already said that the Earth formed around 4.5 billion years ago, and that's when we started to see this layering. So the Earth's mantle started forming around the core, and as it slowly cooled, it became like porridge as the gases sort of started to leave and became more viscous or thick. But there's been a lot of research into when the inner core formed, and this research spans from, it could have been 2.5 billion years ago up to 0.5 billion years ago, based on the behaviour of Earth's magnetic field.
That's quite recent, isn't it? The point that's 500 million years ago.
Yeah, exactly. Yeah, it's very recent in geological terms. And now, if you remember, the Earth's magnetic field is generated by this iron-rich outer core that's circulating around. And in 2019, in a paper in Nature Geoscience, it looked at rocks that were 565 million years old and observed using magnetic minerals, which preserves the evidence for the ancient magnetic field in the rock.
Okay.
They could see that we know that the magnetic field changes over time, but using this magnetism preserved in the rock record, we can see that there was a period, 565 million years ago, where the intensity of Earth's magnetic field was very, very low. So it's 10 times lower than the current Earth's magnetic field. And this correlates, or it's been hypothesized that this relates to a very, very young inner core.
Okay, so just to go back, how do you get magnetic data from a rock?
Right, so essentially minerals within rocks have something called domains within them that align to the Earth's magnetic field. So as it cools and crystallizes, if the rocks are magnetic, these domains align to the field, and or whatever point of time, so the Earth's magnetic field changes and flips over time, and it has a different inclination and declination. So the angle of the magnetic field changes, and so you can see this angle or the direction based on minerals within the rock.
Okay, a bit like iron filings around a bar magnet.
Exactly that.
Okay.
Yeah. Another point about the inner core is that, so the inner core that's encapsulated by this liquid outer core, which allows it to rotate independently from the Earth itself. And that's due to the effects of the Earth's magnetic field and the effects of gravity between the core and the mantle. And so scientists have used seismic waves that travel through the Earth to see that the rotation of Earth's inner core changes over not millions of years, but over decades.
Right, so really short.
So really short time periods. And a paper published in Nature Geoscience this year, in January this year, this paper shows that this rotation has recently paused, or is very, very slow, and may experience a turning back relative to the mantle in the next decade or so. And actually, this doesn't sound that relevant to life on Earth, but it has a knock-on effect, because it's not just changes in the magnetic field, but also might affect the length of day. And I'm not quite sure about the reasoning, but from reading around it, it seems that when the spin of the inner core is slower, the gravitational pull on Earth's mantle is larger, which slows down Earth's rotation, which makes the day last a little longer. And if you look at, there's a paper published in PNAS, the Proceedings of National Academy for Sciences, of the United States of America, 2018. 1.4 billion years ago, the day on Earth would be less than 19 hours.
Gosh,
so the day's getting slightly longer.
Not even. Are they getting longer? That's all right then.
Yeah, which is slightly nice in the summer, but in the winter that's dreadful.
Yeah.
And incidentally, I read this, and I thought it was quite cool, is that apparently the force of the wind against mountains changes the length of day by a millisecond over an entire year.
That's quite interesting. That's more substantial than I would have thought.
Yeah. So,
Yeah.
I mean, either we have to change our clocks and everything, but it's kind of interesting.
Yeah.
Just the wind has that power against the mountains.
It just kind of shows how dynamic the Earth is and how complex Earth systems, planetary systems are.
Yeah.
Just makes our lives much harder, really, trying to work out what's going on.
Yeah, exactly.
But all the more interesting, so much more to discover.
I mean, did you find out anything about the length of day and how that's affected by the inner core? Or it seems that it's quite not well established?
There seem to be couplings between all these different processes going on. So between electromagnetic forces and gravity and the mantle interacting with the inner core and the inner core interacting with the outer core and the outer core interacting with the mantle and all these sorts of things. So it seems to be a system that I struggle to understand.
Yeah.
Why it affects that.
It's also not easily accessible, is it? Like, you can't just look at it. I mean, you that's why we're using stuff like seismic waves and analogous planets potentially, or meteorites and stuff to have a look at. Which leads us on to our next point, is that how do we know that these layers exist?
Yeah, so I guess one of the places to start is with the mantle. So how do we know what the mantle's made of, kind of how big it is, why it's there, things like that. And so one of the ways we can access the mantle is through volcanoes. So volcanoes give us extrusion of material from deep in the earth at the surface. And so magma from volcanoes is typically sourced from the mantle. So we've got molten rock coming from depth and coming to the surface and being extruded. Now, there are processes that are occurring as that molten rock comes to the surface that are changing its composition. So we need to be able to account for them to work out what the mantle is actually made of. But volcanoes can give us a really kind of looking glass into what the layers of the earth are made of. But we also have things called xenoliths. Now, these are little chunks of rock trapped inside of other rocks. So xeno, kind of that phrase often means just like foreign. Lith means rock, so like foreign rocks. So that might be rocks that are forming close to the surface, are actually including and encapsulating rocks that are formed much further down into the earth within them.
They're foreign objects, essentially.
Yeah, absolutely. Yeah.
They have no right to be there.
Yes.
But they are.
They are there. Yeah, and recently I saw some mantle xenoliths in Sardinia where you had beautiful kind of olivine and pyroxene crystals. So these are minerals that are found in the mantle, had lovely green colours within kind of volcanic rocks or igneous rocks that are forming closer to the surface. Another example of this are diamonds. So they form in the upper mantle, about sort of 150 kilometres beneath the surface, but then they can be brought to the surface within other rocks.
Another one of those is, well, not really a xenolith, but is an ophiolite.
Okay.
And an ophiolite is a segment of oceanic crust that is found on continental crust. So so you mentioned that two plates, like oceanic and continental, can collide, and that the oceanic would sink underneath the continental crust because it's denser.
Yeah.
Well, sometimes a bit of oceanic crust gets scraped off. A little tiny bit is scraped off the oceanic crust and is what's called abducted. So it gets carried up onto this continental crust and pushed up. And so you see these ophiolites in mountains because it's been formed by these tectonic processes and it's been carried up these mountains essentially.
I've seen one of the most famous ophiolites is in Cyprus, and it's kind of an inverted sequence. So at close to sea level you see sediments, and then as you climb up into the mountains you're kind of going deeper into the earth. So you kind of travel through the crust until you reach the mantle, and you see some really beautiful minerals that are formed within the mantle. It's a great sequence.
Yeah, it's great. Also, for anyone that doesn't want to go to Cyprus, there's one I know. I think there's one in Scotland actually, but I think there's also one in Cornwall.
Oh, really?
At Coverack Cove.
Wow.
It's beautiful. Yeah. I did my master's project there.
Oh,
so you
nice.
can walk along the beach and walk through Earth's layers.
That's awesome.
Which is very cool. The other way in which scientists know that these layers exist is through seismic waves. So an earthquake that occurs on the surface, the shock waves spread not just on the surface like we see these tremors, but they also spread within the earth themselves. in numerous directions. So we see surface waves. So that's what forms, that's what creates buildings to collapse and cause mass destruction. But you also have body waves, and these travel through the mantle. And the speed at which they travel are dictated by density differences through temperature and rock type. So these waves are called P and S waves, and the P waves can travel throughout liquid, gases and solids, but S waves are unable to travel through fluids or gases. So if an earthquake sends waves travelling through the earth, we have these instruments placed around the earth to detect these P and S waves. And through them you can identify seismic discontinuities. So for example, there's something called the Moho discontinuity, which is the boundary between the crust and the mantle. And you've also got the Gutenberg discontinuity, which is the boundary between the core and the mantle. And it's important because P waves are strongly refracted or bent when they travel through this boundary. But S waves can't travel through fluids, and the outer core is fluid. So they disappear. So some instruments don't record the S waves. So from that, scientists have been able to detect, or seismologists have been able to detect, that there must be something liquid inside the Earth, and that's the outer core.
Okay, so just to recap, we've got these two waves that are formed by various processes within the Earth, namely earthquakes. We've got our P waves and our S waves. P waves can travel through anything. S waves can't travel through fluids, so liquids or gases.
Exactly.
And so by looking at which waves arrive at us from a given earthquake, for example, we can start to map out what these waves must be travelling through within the Earth. And so we know what those layers in the Earth are in terms of their phase.
Exactly. And it's important to know that the P waves are called primary waves, and they tend to arrive first, and then S waves are secondary because they arrive afterwards.
Okay. So we've got all these techniques for working out what the Earth's layers are made up of, but we can also use planetary science to understand about the Earth, because some objects in space, some celestial objects, form in similar ways, and we think actually asteroids are kind of the leftovers from the planet building process that didn't form planets. And one particular interesting one of the asteroids is called 16 Psyche, and we actually have the Psyche mission run by NASA that's going there. So Psyche is a metal asteroid. So we think this will represent the differentiation process where rocks have separated into that core that is mostly iron and nickel. We get metallic meteorites, like just metal in meteorites getting our iron and nickel. And we think that Psyche is an example of a planetary core that didn't then form into a planet. It might be that we had the kind of silicate material stripped away. So we can use these materials to understand the Earth, and we can even use the moon to understand the timings of changes going on in the Earth by looking at its chemistry. And if we assume, which is what we think happened, that the moon formed from the Earth and an impactor, so mostly formed from material from the Earth, we can look at similarities and differences in the chemical composition of these two planetary bodies to work out what the timings were of the moon forming event and planetary differentiation.
Nice. Incidentally, I've got a fact about the moon that I found out yesterday.
Right.
Australia is wider than the moon.
Surely not.
Well, a moon is 3,400 kilometres in diameter, and Australia is 4,000 kilometres. Do you know where I found the fact?
Go on, do tell.
The dating app Thursday. Okay. I don't know why. It's a weird source of scientific information.
It is. Is it rigorous?
It's just relentless.
Is it
Thursday.
peer reviewed?
Only on Thursdays.
Okay.
They just keep pumping out these different facts, and maybe it's just a little party piece you can say on a date. But I think it's a bit lame, isn't it?
No, I like it. I mean,
did you know?
It makes me think. I feel like I want to go and look at a map of the world and the moon and compare these two. I don't know if I believe your fact, but I do believe you because I trust you.
That's nice, yeah. Okay, so the last section we're going to go through is how does this tie into everyday life and why is this important? So that fits our brief of the core of everything. So these layers are crucial for life on Earth. The spin of the iron and nickel outer core produce a magnetic field around the Earth, which is due to the movement of electrically conductive materials. And from a 2D perspective, these look like two massive ears on the world.
That's
around
really
the
nice.
world.
I've not heard it described like that before. But
No,
that
I
is
thought
a,
it, I
that
thought
is
it
a
this
great
morning.
image.
But yeah, massive ears like the BFG, because the ears are basically bigger than the planet.
Yeah, fair.
And this magnetic field, which is known as the magnetosphere, is distorted by solar winds, which are ejected by the sun.
Yeah, and actually, the interaction between these solar winds and the magnetosphere forms a phenomena that we are really familiar with. So the solar wind is made up of ejected particles, and when these particles, these high energy particles, get trapped in the Earth's magnetic field, they collide with air molecules, and their energy levels are changed in these elemental particles that are arriving. And as those energy levels relax, they release photons. Photons are just packages of light. And so that's what gives us colours in the atmosphere. And this is what produces the aurora borealis, or the northern lights. And we also get a similar effect down in the southern hemisphere, giving us the aurora australis, or the southern lights. And this phenomenon isn't just limited to the Earth. So we also get aurora on other planets too. And I think there's some really beautiful images. I'd just go and Google aurora on other planets, because there's some amazing images of seeing these.
Are they all similar colours?
I think we get different colours because of the elements that we have in the atmosphere. So I think oxygen produces red, and so different planetary atmospheres are made of different elements. They have different compositions, and so we get different colours.
Yeah, exactly. That's really interesting. But the magnetic field itself is actually important as well, because compasses for navigation use the magnetic field. That's what the needle spins around. But the magnetic field, as we mentioned earlier, flips in direction every few 100,000 years, although it's quite variable. And we don't really know why that occurs, why this flip occurs, but it's just believed to be due to processes within the core. And you see this in the rock record. As I mentioned earlier on, as rocks cool and solidify, the magnetic components within the rock align to the Earth's magnetic field. And based on the direction of these alignments, you can see how the Earth's field is flipped. So over time, our compasses will change direction gradually. And so you'll end up having, north pointing south and south pointing north. And the other point is that it's important because birds and other lots of sea life use the magnetic field. They have internal compasses that use the magnetic field to navigate. So the question is, what on earth will happen to the birds when the Earth's magnetic field flips?
That's such a great question.
It's chaos.
What does happen? Does everything just migrate in the opposite direction? Do we get penguins at the North Pole and polar bears at the South Pole?
But what if it's gradual, these flips? So what happens in the midpoint? Do they just diagonally collide into each other and it's just absolute mayhem?
Everything just converges on the equator, not really knowing where to go.
Yeah, exactly. It's just a massive
magnetic purgatory.
Tailbacks of birds. Yeah, absolutely no idea.
Wow. When do we know when this might happen next?
In my head we're due one, but that could be. I could be mistaken.
I just want to know if I should get my camera ready to go see what the birds are doing. Take their lead.
Yeah. When they start just accidentally flying into each other, that's when you know.
Yeah, they're very true. But the magnetic field is so important, not just for birds, but also for humans, because it protects us from this solar wind. So these high energy particles coming from the sun, that they would otherwise be eroding our atmosphere. Actually, they're deflected or kind of attenuated by this magnetosphere. And so it kind of protects us, because if we didn't have that protection, it would actually cause chaos with a lot of our sort of technology and electrical systems, because magnetic fields can interact with electrical systems via electromagnetism. And sometimes when there is particular sort of solar activity, like solar flares emitting a lot of these high energy particles, they can affect things like energy systems. And there's a lot of research going on into that. So we need this magnetosphere to protect us. Otherwise, we'd be in trouble without it, basically.
But we can also use our layers to explore, the layers of our planet to explore the great beyond.
Yes, yeah. So one particular sphere of research at the moment is exoplanets. So these are planets within other solar systems, so planets orbiting other stars, many light years away typically. And by understanding what the Earth is like and how it formed, we can start to build up a picture of what these exoplanets might be like, what might be underneath their atmospheres. If we can't see their atmospheres, what might be going on at the surface. And this all fits into that big question of, is there life elsewhere, or are these other planets, these exoplanets, habitable?
And that is an absolutely leading question in today's world, isn't it? And so, yeah, from the rotating solid inner core, travelling through to the liquid outer core, through to this bulky, viscous, porridgey mantle, to the creme brulee crust, we've about covered the layers of Earth, I'd say.
Almost as a meal.
Almost
as a satisfying structure.
That sounds quite nice, porridge and creme brulee.
Yeah.
So thanks so much for listening, everyone.
See you next time.
See you next time. And next time we'll be looking at mass extinctions.
Let's hope the magnetic field doesn't flip in the meantime.
Ciao.